Good afternoon, everyone. Today we will be talking about the cross product of two vectors. We talk about the scalar product of two vectors. Now we talk about the cross product of two vectors, also known as the vector product of two vectors, as opposed to scalar, the one that we have studied already. Okay, so let's get started. Let's see what it means. The cross product, when we talk about this cross product or the vector product of two vectors, A and B, so let's consider vector A, the black one over here, and the vector B, the black one over here, the blue one, sorry. The cross product is a vector that is perpendicular to both vectors A and B. So I'm looking for a certain vector C that has a very important quality. It is perpendicular both on vector A, perpendicular on A, and C is also perpendicular to B. Please let's remember that. C is perpendicular both on A and on B, which means it's basically perpendicular to the plane made with vector A and vector B. So basically what I need to look for a vector C, which could be this vector over here, that is perpendicular to A and B. Obviously, there are lots and lots of vectors that are perpendicular to A and B. It depends on the magnitude, right? So it can be that big, even bigger, small, or nothing stops me from going in the opposite direction. So lots and lots of vectors. Now, let's take a look together at the following simulation. We're going to see what happens when with vectors perpendicular to two vectors A and B. So let's see if I can get, okay, so the simulation is here. Hopefully everything works nicely. Let's get to it. No big deal, there you go. Did I get there? There you go. Good. So you have an example here of two vectors A and B and vector C that is perpendicular to them. Please notice the plane made up of vectors A and B. And I'm going to play a little bit with vector A and vector B, and I want you to notice what happens with the cross product with vector C becomes bigger and smaller. Let's play with B a little bit. Let's play with B a little bit. Let's see what happens. Vector B. There you go. I play with vector B, and now I put vector B on top of vector A. Look what happened with vector C. Now I'm going to continue to move my vector B, and it seems like vector C, the perpendicular one, disappeared. Now let's take a look what happens below my plane. Just look what happened. Vector C is still there, perpendicular. It's just that it's an opposite direction. Let's continue playing a little bit with vector B. There you go. You start seeing it on the other side of the plane. So there you go. This is how vectors perpendicular to vector A and B look like. Good. So let's go back to our page. And what we are trying to do right now, we are trying on some specific examples to figure out a vector perpendicular to A and B. So what I said, The cross product is nothing else but a vector C that is perpendicular to both of them. And the notation used is vector A cross vector B. The result of this operation will be a vector as you have seen in the simulation as well as in my diagram right here. This is vector C. Okay, so what we want to do, we want on an example to find the cross product of vectors A, you have the coordinates there, and vector B. Vector A is this one. I know this diagram doesn't represent those vectors, but right now it doesn't really matter. The only purpose I have with this diagram is to show you that I am looking for a red vector C that is perpendicular both on A and on B. So I am looking for a certain vector C unknown, which is nothing else but the cross product of A and B. This is unknown. What I know for sure is that it is a vector. Now, whenever I deal with a vector and it's unknown, let's call it, for example, x, y, and z. The coordinates of C are x, y, and z. What do I know about C? I know that C is perpendicular to vector C is perpendicular to A. What does it mean? It means that the scalar product of C and A must be equal to 0. Now, how can I rewrite that? C times A dot product of C and A will be 2x plus y equals 0. So that is my first relationship here. 2x plus y equals 0. Now, another thing that I know is that vector, I know this is unknown. Let's move things around a little bit. I also know that absolutely identical to what I did here, I know that vector C is also perpendicular to vector B, which means the dot product of C and B must be equal to 0. Let's write together the dot product of C and B. X times negative 1, so that's a negative x, plus 2 times y, plus 5 times z equals 0. There you go. I have a second expression here. Do not forget, my objective is to find a vector C given by x, y, and z. Let's see if we can manipulate this a little bit. And I shouldn't be surprised if I got more than one vector. What I'm going to do from number 1, this is number 1, and this is number 2. From 1, I'm going to isolate y, let's say y. Y equals negative 2x. And with this, I'll substitute into 2. Let's substitute into 2, and let's see what happens. It's going to be minus x plus 2 times y, but instead of y now I have negative 2x plus 5z equals 0. Okay, so let's see what happens. Here I have a minus negative x minus 4x. That's a negative 5x plus 5z equals 0, which means z, I can write z in terms of x as well, will be z equals x. So I have z equals x, y equals negative 2x. Let's see, how would I write the vector C right now? Remember, vector C is x, y, and z. X, y, and z written on components. Now, let's see what I got. C is x stays the same, nothing I can do. my y is negative 2x, and my z is x. Please notice that x is common on in all three components, so I can rewrite this as x times 1, negative 2, and 1. Now let's analyze what this relationship is telling me. It's telling me that, for example, for x equals 1, I get a certain vector c, which is 1, negative 2, and 1. What do I know about this vector? I know it's perpendicular both on A and on B, perpendicular on both. For x equals, I don't know, negative 2, for example, c will be a vector, let's calculate, negative 2, 4, and negative 2. What do I know about this c? It's again perpendicular to A, perpendicular to B. Not a surprise. Good. And lots, infinite number of vectors that are perpendicular to my vectors, initial vectors A and B. Now, what happens, x is a real number. Usually, for x, I use a different notation. I use k. K seems a typical notation for a real number. As a result, x, y, and z can be written as y will be negative 2k, and z will be k. Okay, so as a result, c can be rewritten. I do exactly the same thing. I just rename my x as k. K times 1, negative 2, and 1. And again, for different values of k, which is a real number, I'll get different c values. The cross product is the one for k equals 1. So when k equals 1, that will give me c, will be my dot product my cross product A and B. So there you go. This is how we found the cross product of two vectors. Now, what we're going to do in class, we're going to generalize for any vectors A and B. Please notice that right now we only did this for some special vectors A and B that I picked. Our objective is to do the same thing for any vector in the world.